Different people may have different opinions about perfect life. What is a perfect life? Is there one thing that would make your life perfect? The answer is, there is no such thing as perfect life. Nobody is perfect. Imperfections are always there. When we visualize, we find that in imperfections, crystals resembles with our life. It is very difficult to have a perfect crystal. Crystals have few imperfections due to arrangement of atoms in it. It is known as imperfections in solids.
ਹੈਲੋ ਵਿਦਿਆਰਥੀਓ, ਸਾਡੇ ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚ ਜੀ ਆਇਆਂ ਨੂੰ। ਸਾਡਾ ਅੱਜ ਦਾ ਪਾਠ ਹੈ ਪੁਆਇੰਟ ਡਿਫੈਕਟਸ। ਸਾਡੇ ਪਹਿਲੇ ਵਿਚਾਰ ਵਟਾਂਦਰੇ ਵਿੱਚ ਅਸੀਂ ਇਲੈਕਟ੍ਰੋਨਿਕ ਅਤੇ ਪਰਮਾਣੂ ਤਰੁੱਟੀਆਂ ਬਾਰੇ ਪੜ੍ਹ ਚੁੱਕੇ ਹਾਂ। ਪਾਠ ਸ਼ੁਰੂ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਸਿੱਖਿਆ ਮਨੋਰਥਾਂ ਤੇ ਇੱਕ ਝਾਤ ਪਾਈਏ।
ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ। ਇਹ ਪਾਠ ਪੂਰਾ ਕਰਨ ਤੋਂ ਬਾਅਦ ਸਿੱਖਿਆਰਥੀ ਇਹ ਕੁਝ ਕਰ ਸਕਣਗੇ। Discuss point defects in stoichiometric and non-stoichiometric crystals. Give consequences of Schottky and Frankel defects. Explain metal excess and metal deficiency in non-stoichiometric defects. Discuss cation vacancies and anion vacancies. Discuss extra anions and extra cations occupying interstitial sites. Mention consequences of metal excess defects and metal deficiency defects.
Point defects. Students, today we will discuss point defects in detail. ਆਮ ਤੌਰ ਤੇ ਅਸੀਂ ਦੋ ਤਰ੍ਹਾਂ ਦੇ ਡਿਫੈਕਟਸ ਨੂੰ ਪਛਾਣਦੇ ਹਾਂ, ਪੁਆਇੰਟ ਡਿਫੈਕਟਸ ਅਤੇ ਲਾਈਨ ਡਿਫੈਕਟਸ। ਸਾਧਾਰਨ ਸ਼ਬਦਾਂ ਵਿੱਚ ਅਸੀਂ ਕਹਿ ਸਕਦੇ ਹਾਂ ਕਿ ਇਹ ਦੋਵੇਂ ਤਰ੍ਹਾਂ ਦੀਆਂ ਤਰੁੱਟੀਆਂ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਵਿੱਚ ਪਰਮਾਣੂਆਂ ਦਾ ਅਨਿਯਮਿਤ ਵਿਸਥਾਰ ਹੋਣ ਕਰਕੇ ਪੈਦਾ ਹੁੰਦੀਆਂ ਹਨ। ਜੇ ਤਰੁੱਟੀ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਦੇ ਕਿਸੇ ਇੱਕ ਬਿੰਦੂ ਤੇ ਮਿਲਦੀ ਹੈ ਤਾਂ ਇਸ ਨੂੰ ਪੁਆਇੰਟ ਡਿਫੈਕਟਸ ਜਾਂ ਬਿੰਦੂ ਤਰੁੱਟੀ ਆਖਿਆ ਜਾਂਦਾ ਹੈ, ਜਦਕਿ ਜੋ ਅਨਈਵਨ ਡਿਸਟ੍ਰੀਬਿਊਸ਼ਨ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਦੀ ਪੂਰੀ ਰੋ ਵਿੱਚ ਹੁੰਦੀ ਹੈ ਤਾਂ ਇਸ ਨੂੰ ਲਾਈਨ ਡਿਫੈਕਟ ਜਾਂ ਪਾਲ ਤਰੁੱਟੀ ਆਖਿਆ ਜਾਂਦਾ ਹੈ। ਇਹਨਾਂ ਤਰੁੱਟੀਆਂ ਨਾਲ ਕ੍ਰਿਸਟਲ ਦੀ ਸਿਮੈਟਰੀ ਤੇ ਵੀ ਅਸਰ ਪੈਂਦਾ ਹੈ। ਪੁਆਇੰਟ ਡਿਫੈਕਟਸ ਨੂੰ ਤਿੰਨ ਵਿਭਾਗਾਂ ਵਿੱਚ ਕਲਾਸੀਫਾਈ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਪੁਆਇੰਟ ਡਿਫੈਕਟਸ ਇਨ ਸਟੋਕਿਓਮੈਟ੍ਰਿਕ ਕ੍ਰਿਸਟਲਸ, point defect in non-stoichiometric crystals, impurity defects. There are two types of point defects in non-ionic solids. These are vacancy defects and interstitial defects. We will discuss them one by one. First, let's discuss vacancy defects. Vacancy defect. Those crystals which have vacant lattice sites show vacancy defects. Those lattice sites in a crystal which have no atom or ion are considered as vacant or empty. This defect affects the density of the substance. Because of vacancy defects, density of the substance decreases. When a substance is heated, it develops vacant sites in crystal lattice. Interstitial defect. ਅਜਿਹੇ ਰਵੇ ਜਿਨ੍ਹਾਂ ਦੀਆਂ ਦਰਾੜਾਂ ਜਾਂ ਤਰੇੜਾਂ ਵਾਲੀ ਥਾਂ ਤੇ ਪਰਮਾਣੂ ਹੋਣ, ਉਹ ਇੰਟਰਸਟੀਸ਼ੀਅਲ ਤਰੁੱਟੀਆਂ ਪ੍ਰਦਰਸ਼ਿਤ ਕਰਦੇ ਹਨ। ਇਸ ਤਰੁੱਟੀ ਕਾਰਨ ਪਦਾਰਥ ਦੀ ਘਣਤਾ ਪ੍ਰਭਾਵਿਤ ਹੁੰਦੀ ਹੈ। ਇੰਟਰਸਟੀਸ਼ੀਅਲ ਤਰੁੱਟੀਆਂ ਕਾਰਨ ਪਦਾਰਥਾਂ ਦੀ ਘਣਤਾ ਵੱਧ ਜਾਂਦੀ ਹੈ। We have discussed vacancy and interstitial defects. It is time to discuss point defect in stoichiometric crystals. Point defects in stoichiometric crystals. Those defects which don't disturb the stoichiometry of the solid are known as intrinsic or thermodynamic defects. Before continuing our topic, it is important to know what stoichiometry is. Stoichiometry rests upon law of conservation of mass. Stoichiometric compounds have exactly the same ratio of ions as shown in their chemical formulas. In simple words, we can say that they have equal number of cations and anions. Point defects in stoichiometric compounds do not disturb the stoichiometry of the solid. Stoichiometric compounds show two types of point defects. These are Frankel defects and Schottky defect. Frankel defects ਇਸ ਡਿਫੈਕਟ ਦੀ ਖੋਜ ਰੂਸੀ ਵਿਗਿਆਨਿਕ ਫ੍ਰੈਂਕਲ ਨੇ 1926 ਵਿੱਚ ਕੀਤੀ। ਜਦੋਂ ਕੋਈ ਆਇਨ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਵਿੱਚ ਐਕਚੁਅਲ ਪੋਜੀਸ਼ਨ ਬਦਲਦਾ ਹੈ ਤਾਂ ਫ੍ਰੈਂਕਲ ਡਿਫੈਕਟ ਪੈਦਾ ਹੁੰਦਾ ਹੈ। ਫ੍ਰੈਂਕਲ ਡਿਫੈਕਟ ਅੰਦਰ ਆਇਨ ਆਪਣੀ ਨਾਰਮਲ ਸਾਈਡ ਤੋਂ ਹਟ ਕੇ ਇੰਟਰਸਟੀਸ਼ੀਅਲ ਸਾਈਡ ਤੇ ਆ ਟਿਕਦਾ ਹੈ। ਨਤੀਜੇ ਵਜੋਂ ਫ੍ਰੈਂਕਲ ਡਿਫੈਕਟ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਵਿੱਚ ਐਟਮ ਦੀ ਐਕਚੁਅਲ ਪੋਜੀਸ਼ਨ ਤੇ ਵੈਕੈਂਸੀ ਡਿਫੈਕਟਸ ਪੈਦਾ ਹੋ ਜਾਂਦਾ ਹੈ ਅਤੇ ਕ੍ਰਿਸਟਲ ਲੈਟਿਸ ਵਿੱਚ ਇੱਕ ਨਵਾਂ ਇੰਟਰਸਟੀਸ਼ੀਅਲ ਡਿਫੈਕਟ ਬਣ ਜਾਂਦਾ ਹੈ, ਪਰ ਕ੍ਰਿਸਟਲ ਇਲੈਕਟ੍ਰੀਕਲੀ ਨਿਊਟਰਲ ਹੀ ਰਹਿੰਦਾ ਹੈ। Schottky defect. This defect was discovered by a German scientist Schottky in 1930. This type of defect arises due to missing of atoms or ions from its actual lattice sites, but the crystal remains electrically neutral here. It contains equal number of missing cations and anions. This defect creates cations and anions vacancies in a crystal lattice. Look at this chart. We will discuss consequences with the help of this chart. Let's discuss consequences of Schottky and Frankel defects. These defects affect other properties of crystals like electrical conductivity, density, lattice energy, and dielectric constant of the crystal. These defects increases the electrical conductivity of the crystals. What happens when we apply electric field on a crystal having these defects? On applying electric field, we see that ions move from its normal lattice site and creates a hole in a crystal lattice. The hole moves from one position to another position of a crystal lattice as they are in a chain and helps in conduction of electricity. Due to the presence of these holes, density of crystal decreases, but it is seen only in case of Schottky defect. Due to the presence of these holes, lattice energy or stability of a crystal decreases. In case of Frankel defect, the dielectric constant of the crystal increases. Let us compare Schottky and Frankel defects with the help of a animated chart.
Schottky defect is shown by compounds having equal size of cations and anions and high coordination number, whereas Frankel defects are shown by compounds having larger anions than cations and low coordination number. Schottky defects decreases the density of this crystal, whereas Frankel defect does not affect the density of crystals. Schottky defect arises due to missing of atoms or ions from their normal crystal sites. Frankel defect arises because of displacement of atoms or ions from their normal sites and occupy interstitial sites. Examples of compounds showing Schottky defects are sodium chloride, that is NaCl, and CaCl, cesium chloride. Examples of compounds showing Frankel defects are AgCl, that is silver chloride, and ZnS, that is zinc sulfide.
Point defects in non-stoichiometric crystals. How can we define non-stoichiometric defects? Before defining non-stoichiometric defects, it is essential for us to know about non-stoichiometric compounds. Let's try to define it. Non-stoichiometric compounds are those in which the number of cations and anions are not exactly in the ratios as indicated by their chemical formulae. Example of non-stoichiometric compounds is vanadium oxide. The imperfection in such type of compounds are known as non-stoichiometric defects. Point defects in non-stoichiometric compounds are of two types: metal excess defects and metal deficiency defects. First of all, we will discuss metal excess defects. Later on, we will focus on metal deficiency defects. Metal excess defects: anion vacancies, excess cations occupying interstitial sites. What are metal excess defects in solids? In this section, we will learn about metal excess defects in solids. In metal excess defects, positive ions exist in excess. There may be two ways for causing such type of defects. What are these two ways? These are anion vacancies and excess cation occupying interstitial sites. Anion vacancies. In this type of metal excess defect, negative ions may be missed from their lattice sites and creates holes in crystal lattice. These holes are filled with the help of electrons. Such electrons which are trapped in the ionic vacancies are known as F centers. This word F center is derived from the German word Farbener Center, which means color center. In this way, we see that F centers are responsible for imparting color to the crystal. When alkali metal halides are heated in an atmosphere of alkali metal vapors, anion vacancies are produced. F centers are paramagnetic due to the presence of unpaired electrons. The common example is sodium chloride. Let's take other example of it. Excess of lithium in lithium chloride gives us a pink color. Excess of potassium in potassium chloride makes it violet. This defect is found in crystal having Schottky defects. These solids are electrically neutral. These have equal number of cations and anions.
Anion vacancies. Let us take an example of sodium chloride. In a crystal of sodium chloride, that is NaCl, sodium ions, that is Na positive, and chloride ions, that is Cl negative, ions are there. Here, sodium ions are shown by the symbol A positive and chloride negative ions are shown by the symbol B negative. When it is heated in an atmosphere of sodium vapor, the large number of sodium atoms are deposited on the surface of the crystal. Chloride ions diffuses to the surface where they combine with the sodium atoms, which lose the electrons. The electrons diffuse into the vacant site created. The electrons absorb some energy from the white light and re-emit the yellow color.
Excess cations occupying interstitial sites. In this type of metal, excess defect, they have extra positive ions at interstitial sites. These are balanced by the electrons at other sites. It is seen in the non-metal atoms which leave their electrons behind. These are also electrically neutral. Let's discuss an example of such type of defects. If zinc oxide is heated, it loses oxygen and turns yellow. The excess of electrons get trapped into the hole generated due to the liberation of anion 1/2 oxygen and Zn2 plus zinc ion retain their portion. It turns yellow when hot and white when cold. Crystal with either type of metal excess act as semiconductors.
Students, let us have a look at metal excess defect. In case of excess cations occupying interstitial sites, this defect is formed in only those crystals which can develop Frankel defects. In this image, number of extra anions is equal to the number of additional electrons at interstitial sites. The common example of excess cations occupying interstitial sites is zinc oxide, that is ZnO.
Semiconductors. N type of conductors. Semiconductors are of two types, N and P type. First, we will discuss N type semiconductors. As we know, silicon and germanium are tetravalent atoms having 4 valence electrons. These can be doped with pentavalent group. 15 elements like phosphorus, arsenic. The reason is that pentavalent group elements have 5 valence electrons. After doping, we see that doped semiconductor contains an unsatisfied valence electron. In other words, we can say one valence electron of pentavalent atoms remains free after bonding. This free electron helps in increasing the electrical conduction of the semiconductor. It is known as an N-type conductor. The symbol N refers to negative here, which is used for electron. The free electron is responsible for conduction.
The position of silicon in the periodic table has been shown. The three-dimensional structure of silicon has been shown along with the tetrahedral coordination. The process of doping has also been depicted by deliberate addition of impurities in the pure silicon crystal. Further, N and P-type semiconductors are shown to be formed with the addition of arsenic and boron impurities respectively.
P-type of semiconductors. As we know, the tetravalent silicon and germanium have 4 valence electrons in their outermost shell, and trivalent element, group 13 element, example aluminium, gallium, got have 3 valence electrons in their outermost shell. When silicon or germanium is doped with the prevalent impurities, it results in the formation of a hole. This hole is known as electron deficient center. It also helps in increasing the conduction of electricity through the doped semiconductor. This is known as a p-type of semiconductor. 12-16 compounds. When a solid state compound is formed by combination of elements of group 12 and 16 of the periodic table, these compounds are called 12-16 compounds. Examples of these compounds are zinc sulfide, cadmium sulfide, etc. 13-15 compounds. When solid state compounds are formed by combination of elements of group 13 and 15 of the periodic table, these compounds are known as 13-15 compounds. Examples of these compounds are AlP, aluminium phosphide, GaAs, gallium arsenide, InSp, indium antimonide, etc.
Let us discuss extrinsic semiconductors. Addition of arsenic in silicon is shown here. There are presences of excess electrons in it, which take part in conduction. Let us see addition of boron as impurity in silicon. We can see holes there. The formation of a hole has also been visualized as the vacancy of an electron.
Metal deficient defects. Cation vacancies. Excess anions occupying interstitial sites. Metal deficient defects contain less number of positive ions than negative ions. These are of 2 types: cations vacancies and excess anion occupying interstitial sites. First, we will focus on cation vacancies. Cation vacancies. In such type of metal deficient defects, few of the positive ions may be missed from their lattice sites. These missed positive ions create vacant site in a crystal. The extra negative charge may be balanced by 2 nearby positive charges on an ion. In such type of cases, metal ions acquire 2 positive charges instead of 1. The common example of metal deficient defects having cation vacancies are ferrous oxide and nickel oxide. Excess anions occupying interstitial sites. In excess anions occupying interstitial sites, there are extra negative charges. These are balanced by extra charges on the adjacent metal ions. This type of defect is very common in solids. Impurity defects. These defects are found in ionic crystals. They arise due to the presence of impurity ions at the lattice sites or at the vacant interstitial sites. We find such type of defects on crystallization of molten sodium chloride containing a little amount of strontium chloride.
Calculate the percentage of nickel ions, Ni2 positive and Ni3 positive ions in Ni 0.98 or 1.00 crystal. Solution: Ni 0.98 or 1.00. Let's suppose value of Ni2 positive is x and value of Ni3 positive is 0.98 minus x. As we know, total charge on the compound must be 0, so that 2x plus 3 multiplied by 0.98 minus x minus 2 is equal to 0. 2x plus 2.94 minus 3x minus 2 is equal to 0. Minus x is equal to minus 0.94. X is equal to 0.94. Percentage of Ni2 positive is equal to 0.94 divided by 0.98 multiplied by 100 is equal to 96%. Percentage of Ni3 positive is equal to 4%.
So, today we have discussed point defects in ionic solids. These are of three types: point defects in stoichiometric crystals, point defects in non-stoichiometric crystals, and impurity defects. We have also discussed point defects in stoichiometric crystals, which are of two types: Schottky and Frenkel defects. We have also differentiated Schottky and Frenkel defects. Metal excess defects are of two types: anion vacancies and excess cation occupying interstitial sites. Metal deficiency defects are of two types: cation vacancies and excess anion occupying interstitial sites. If irregularity is found at a point in a crystal lattice, it is known as point defects. So, now we come to the end of today's topic. Here's a quick test for you to find out how much you have actually absorbed. Question number 1. Which point defect lowers the density of a crystal? The answer is Schottky defect. Question number 2. Name the type of point defect that occurs in a crystal of zinc sulfide. Correct answer is Frenkel defect. Question number 3. Name the non-stoichiometric point defect responsible for color in alkali metal halides. The correct answer is metal excess vacancies. Next question. Write a property of solids modified due to structural imperfection. Answer is density. Next question. Give examples of compounds exhibiting Schottky defects. The answer is NaCl and KCl. Question. Give examples of compounds exhibiting Frenkel defects. Correct answer is AgCl and AgBr. Next question. Write a point of difference between Schottky and Frenkel defects. The answer is only Schottky defect lowers the density of the crystal. Next question. Give an example of non-stoichiometric compounds. The answer is vanadium oxide. Next question. Write the name of a crystal having anion vacancies. Right answer is NaCl. Next question. Write the name of a crystal having cation vacancies. Right answer Fes. Next question. Which type of point defect is shown by ionic solids having high coordination number? The correct answer is Schottky defect. Next question. Which type of point defect is shown by ionic solids having low coordination number? The answer is Frenkel defect. Question. What are the ways to form metal excess defects? The answer is metal excess defects. Metal excess defects can be formed by two types. Number 1, anion vacancies, and number 2, excess cations occupying interstitial sites. Next question. What are the ways to form metal deficient defect? Metal deficient defects is the right answer. Metal deficient defects can be formed by two types. Number one is cation vacancies and number two is excess anions occupying interstitial sites. Next question. Why metal excess defects conduct electricity? The answer is metal excess defects conduct electricity due to presence of free electrons. Question. What is the reason behind electric conductivity of N-type semiconductors? The answer is N-type semiconductors show electric conductivity because of presence of free electrons. Next question. What is the reason behind electric conductivity of P-type semiconductors? The answer is P-type semiconductors show electric conductivity because of presence of holes. Well done, students. So I hope that you all have enjoyed today's lesson and also you have learned about imperfections in solids. See you next time. Till then, bye-bye.